All right, this is the Geometry Unit 4, Lesson 5 video over some theorems around congruent triangles. So this is going to be a little bit of a different lesson video simply because there's a lot of material in the actual lesson questions that you're not actually going to be responsible for on the test. They're mostly like proofs. So what I'm going to do is go over the different theorems in the lesson and give you kind of an image visual aid to go along with them. And then I'm going to work through actually the questions in this lesson. I don't do this very often, but I'm going to work through those, and just trust me that when it comes to the test, I will make sure you are kind of prepared for the types of questions you're going to see, because there really isn't a lot on this lesson that it looks like things that are on the test. So we're going to just focus on just understanding concepts. So everything I'm going over is here in the lesson in some form, but I'm going to go through some of my own visual aids that I'm kind of providing for you. So we'll start right here. Oh, actually, we will start here. The first kind of theorem that they discuss is the CP-CTC, and that stands for corresponding parts of congruent triangles are congruent, and actually is a great description of what it tells us. So we just got done doing a bunch of lessons where we were proving that two triangles are congruent. And to do that, we were usually using three parts, right? Like side, 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 side angle, side. Or if we were doing right triangles, hypotenuse, leg, or something like that. So we've been doing that. Well, CP-CTC just is that theorem that allows us to say, okay, once we've proven that two triangles are congruent, then we know that every part of those two triangles that corresponds with each other are congruent. So even though it wasn't one of the parts I used to prove the triangles were congruent, I know that each pair of corresponding sides and each pair of corresponding angles are congruent. And that's pretty much what this slide that you see here says. And as an example, if I proved that ABC and KLM are congruent, no matter what way I proved it, whether it was side angle side or angle angle side, I now know that L and B are congruent, that angle C and angle M are congruent, that side AB and side KL are congruent, for instance. But all the parts of those two triangles are congruent. And that's what CP-CTC means. That's the first one. So I'm going to go through each theorem here pretty much like that. All right, so the next theorem, I'm actually going to draw on this one, is what we call the isosceles triangle congruence theorem. Let me just run over here. Or just the isosceles triangle theorem. So we're going to write that. Let me write that down for us. Isosceles. Isosceles triangle theorem. Again, these are all related to triangle congruence, but we know in isosceles triangles that if we have a triangle and all we know about that triangle is that AB and BC are congruent, and you see that here with these marks. If we know that, then we can prove that the angles A and C are congruent to each other based on the isosceles theorem, because we know that isosceles triangles have this kind of relationship, that the angles here on the base angles are congruent because the sides are congruent. So in other words, if you know the sides are congruent, you can prove that the two angles at the base of that isosceles triangle are congruent. So that's pretty much it. So if you know the sides, then you can prove the angles. Well, what about the other way? Well, there's a theorem for that as well. So if we know that, for instance, the angles are congruent, then we can prove that the sides are congruent. So again, if I know this angle and this angle are congruent to each other, then I know that this side and this side of this are congruent. And this is called the converse of the isosceles triangle theorem. A converse in geometry is a theorem that's derived from another theorem. And it's basically the opposite, the switched version. You rearrange the order. You take the if and the then and you switch them. So earlier, just to kind of drive the point home, we had sides being congruent means angles are congruent. Now we have angles being congruent proves that sides are congruent. So this is the converse of the isosceles triangle theorem. Okay, so the next and kind of the final two are called what we call corollaries. Okay, so a corollary is anything that is a natural outgrowth of another theorem in geometry. And so this one just takes what we know about isosceles triangles and expands it to include equilateral triangles. And we've kind of already talked about this when we first discussed the different types of triangles, but this just states one of these obvious things, that if a triangle is equilateral, meaning all the sides are the same, then it is also equiangular. And if it is equiangular, then it is also equilateral. So that's pretty much it on that one. And so now what we're going to do is go through the different questions on the lesson that apply these different theorems. All right, so let's go look at the questions on the lesson itself. First question, that's vocab. So just go ahead and do that one using the terms and the notes that I just went over. And then this first question is a little bit of a kind of long, kind of drawn out setup, but it is pretty simple when you get into it. So let's look at it together. It says you are a captain of Starship Seleucus from the planet, whatever. I'm not going to read every single one of those. All right. While traveling in a galaxy far, far away, you spotted a previously uncharted red dwarf star at a line of sight of 45 degrees. That is right here in the diagram. So that's this angle here. So 45-degree angle, we're looking at this star. You need to chart the new star, but you couldn't determine its distance from the ship because the star was out of sensor range. After some quick thinking, you remembered that something you learned in geometry that helped you figure out a way to find distance. As the ship continued on its course, AB, you kept watching the star until the line of sight was exactly 90 degrees from the ship. That's point B. 90 degrees and 45 degrees. As the ship continued on its course, you kept watching the star until the line of sight was exactly, read that. The distance you traveled from point A to point B was 125 million retimoleks. From this information, you were able to calculate the distance, BC, to chart the star and chart its position. So let's go through these questions. First, use the triangle sum theorem to calculate angle C. Well, we know we have a 45-degree angle and a 90-degree angle. So if this is 45 and this is 90, and we do 180 minus 90 minus 45 to find the other angle, we get 45 as well. So that means this is also a 45-degree angle right there. All right. So we already know that answer, 45 degrees. So I'll just scroll down and find that. 45, there's F, 45 degrees. I'll also write the answer here, 45 degrees. All right. Based on that, what kind of triangle do you have? Well, if we have two angles that are the same, then that is an isosceles triangle. So that's going to be answer choice L. We have an isosceles. Okay, what does that tell you about the measure of BC? Well, we know that if this is an isosceles triangle, then the two legs have to be the same length. That's coming from the theorems we talked about in this lesson. So it also has to be the same as AB. That's going to be I first. It's choice I. BC is congruent to AB. And then, therefore, the distance is the same, that being 125. So E. That's 125 million. And I'll leave it at that. So that's how you work through that problem. Make sure you get those answers down, and then we'll look at the proofs together. You're not going to be ever responsible for proofs on the tests, so that's why I'm going to work these out. But just kind of follow along and listen along as I go. So we're given ABC as a triangle. We're given the fact that angle A and angle B are congruent to each other. That's a little messy. Angle A and angle B are congruent. That's given. Okay, we want to prove that AC is congruent to BC. Okay, that's these sides out here. Oops, let's erase that. Sorry, I'm making a mess here. We want to prove that these are the same. All right, so let's see what we can get here. Well, we're going to draw an auxiliary line. That's CM right here. They've drawn an extra line down the middle. Then they've done, that's a bisector. Then they've said because of that, ACM and BCM are congruent. So far we have these two congruent angles here, as well as a pair of congruent angles here. You can kind of see where they're going. They're trying to prove that these triangles are congruent. Then they say CM is congruent to CM. That's referring to this line itself. It's congruent to itself. So that's going to be the reflexive property of equality. So let's scroll down here and look for that. We have that in answer choice F. So again, that's reflexive. Then we have ACM. A triangle ACM is congruent to triangle BCM. Well, let's look at what we actually have in those triangles to decide how are we proving that those are congruent. If you look, you see you have angles, you have a side, and you have angles, and the side is not included, so it's angle, angle, side. That's answer choice D. Again, that's angle, angle, side. And then that's our last step, which should be whatever we were trying to prove. So we're going to bring this down here, and that will be AC is congruent to BC. That's answer choice G. All right, so let's look at our last proof down here. This won't take too much time. All right, we have a given of ABC is equiangular, and we want to prove that AB, BC, and CA are congruent. Now, we already know, based on the theorems that we've gone over, that that's true, but how do we actually prove that? Well, first things first, statement number 1 tells us this fact in statement number 2, that those three angles are congruent. So that's going to be the definition of an equiangular triangle, A. Then they say, okay, therefore, AB is congruent to CA. They're using the converse to their isosceles triangle theorem. And then AB is equal to BC, and that's the same, the converse of the isosceles triangle theorem. We're using the same theorem to prove both of those things. And then finally, because of that, we can say that all three of those are congruent, because AB is congruent to both CA and BC. Then we can go ahead and say that all three are congruent, which is answer choice B. And that's the end of that proof. And that's the end of the lesson. So hopefully that is helpful. Like I said, when we get to testing time, we'll be focusing on the important concepts and the types of questions you're going to see. So just, get through this lesson, follow along, and answer these questions, and that'll be all you need for this. And it'll be very similar for lesson 6 as well.